So we are entering statistics, which is, I have written here, statistics is the study of sets of data. So whether you're actually collecting the data yourself or somebody has collected the data already and you're just trying to analyze it, it's a collection of data. So doctors collect data in controlled studies to determine the effectiveness of life-saving drugs. Biologists collect data to observe trends in animal populations. Advertisers collect data to determine what television programs people watch. So data is collected everywhere from a whole bunch of different kinds of people. So a statistic is a number that describes a sample. A lot of times with these we're going to be talking about dealing with the samples because it's virtually impossible to get the full population of something. So when we're talking about those, our symbols that we use, the X with a little bar over it, that stands for your mean. Does anybody remember what a mean is? That's your average. I had a student tell me one time, teachers are mean, they give you your average. That's how they always remembered it themselves. Your mean is your average. The other one we use is our capital SX. That stands for our standard deviation. Your standard deviation is just how far you are from your mean. We'll go through how we get those numbers again. We did do that back in 9th grade also. A parameter, however, is a number that describes a population. So whenever you're being able to look at the entire collection of data for your situation, you're looking at the full population, so your numbers are a little different. You got this little guy that looks kind of like a cursive U that we use for our mean. It's a Greek letter, they call it mu. I always thought it was kind of like my professor was, meowing like a cat every time they said it. I thought it was funny. It's like a little cursive U. And then for our standard deviation this time, they use our sigma x, which is just kind of like an O with a line going off the top to the side. That's your sigma x. That's our population standard deviation. So, population versus a sample. So let's say, for example, somebody is trying to conduct a study to see what the favorite color crayon is for every kindergarten student ever. To get the full population, they would have to survey literally every single kindergarten student across the globe. Is that actually feasible? No. So what they end up doing is, the majority of the time, they end up using just a sample of that population. So a sample is what we refer to as a subset of the population. It should reflect the population.
Okay.
If drawn randomly. And that's one of the big key things with our statistics is whatever group you're dealing with, it needs to be as random as you can possibly make it. Because if it's not a random group of people, then it's going to have what we call bias. Do you guys remember bias? Bias is a bad thing. You don't want to have bias within a study because that means your results are not accurate. So one of the ways you can have bias is by not getting a completely random sample. So then our measures of central tendency. This is a summary statistics used to describe the center of your data. Hence the name, measures of central tendency. Describes your center. So that is your mean, your median, and your mode. Those words sound familiar? Mean, if you're going to calculate it out by hand, you would add up all of your numbers, divide by however many numbers you actually have. That gives you your average. Median is your middle number. And mode is the one that occurs most often. What is there the most in your data set? So those three numbers give us our measures of central tendency. A lot of times they like to ask you which measure is the best measure of central tendency. So your mean is your best measure when there is no outlier. Does anybody remember what an outlier is?
Something that's like really out of like the average range.
It's really far away from the rest of the data. It's this one point that's just kind of randomly out there, doesn't really seem to make sense. What happens when you have an outlier is when you actually go and calculate your average, it makes it inaccurate. It pulls that average either to be higher if your outlier is on the upper end, or it makes the mean be too low if the outlier is on the lower end. So the outlier affects your average. So then your median is your best measure when you have an outlier. Because your median really does not get affected by the outlier being there. It's still going to be pretty much in the same exact spot. So other kind of numbers that we have dealt with and are going to continue to deal with are measures of dispersion. We referred to them as variation in the past, our measures of variation. That are statistics that show how spread out a data set is. So it allows us to see how wide, how spread out that information is. So the numbers we look at to do that would be your range, which is just your high minus your low. That gives us our range. Your lower quartile, which is the 25th percentile. Your upper quartile, which is the 75th percentile. Do you guys remember what percentiles, quartiles are? That's the percentage of data that is below the number you're looking at. So if you're the 25th percentile, that means that 25% of the information is lower than that number. We use percentiles a lot when you're younger and you're going to the doctors. You have to go to the doctor like all the time for these well-kid checkups. They measure your height, they measure your weight, and then they measure how big your head is. So my daughter, I've been doing this for 2 years. She right now is, for her weight, she's in the 43rd percentile. So that means 43% of the kids her age weigh less than she does. And then for her height, she's in like the 47th percentile. So 47% of the kids her age are shorter than she is. Now, since those numbers are near 50, they consider her to be in the average range because she's pretty close to 50. If she was in like the 20th percentile, they would consider her below average because that number is considerably lower. Her head circumference, however, is in the 98th percentile. So 98% of the kids her age have a head smaller than hers is. So we are way above average as far as the size of her head goes, but everything else is about average. So hopefully she'll get caught up to that head size sometime soon. So that's what, as soon as you add that word "ile" onto the end of your percent, that means you're comparing it to everything lower than that. So we break them down into our quartiles because we like to look at the 25th, the 50th, and the 75th. We get a lot of information from those three. Our interquartile range is just subtracting your Q3 minus your Q1. It allows you to look at the middle 50% of the data. So I'll write that little note here. That's your middle 50%. We did a little bit that in 9th grade. We're going to be working with that a lot more now in 11th grade here. Outliers, we already said, those are numbers that are really far removed from the rest of your data. Standard deviation, again, that's how far you are from your mean. And then variance, this is a new word. We haven't dealt with variance before. That is your standard deviation squared. So what do you think you have to do with all these words on this page? Memorize them. Commit them to memory. You got to know those words, so make sure you're studying those. So let's go to our next page. We're going to be working with our measures of dispersion. So as I mentioned, we have two types of standard deviation. You use your little sigma guy when it's the population standard deviation. So you've been using every single thing you can use in your data set. And then you use the little s when it's just a sample of your population that you're dealing with. So when using the calculator to obtain the standard deviation, your work must show the following items. You have to show the number of items that you're using in your data set. You have to show the average. And you have to show the appropriate standard deviation. I say the phrase appropriate because they're not going to tell you whether it's sample or population. You kind of have to pick that up from within the problem. So let's take a look at number 1 here. We have biologists are studying the weight of brown trout in upstate New York streams. They capture and weigh 15 brown trout from the Sawkill Creek in Red Hook, New York. Their weights, accurate to the nearest hundredth of a pound, are given below. So here's the weights of our 15 brown trout. They want us to figure out this information here. So we're going to use our calculator. We are going to go to the stat button right here. Now whenever you want to enter information, which is what we're going to be doing first, we're going to be entering data, you want to go to the edit one. And that creates your lists. We got L1, L2, list 1, list 2, list 3. If you have numbers in there already, the way we get rid of it is you go up to the top so that your L2, in this case, is highlighted. You hit clear and the down arrow and it clears out all those numbers for you. So now I would do the same thing for my L1. I go, hit clear, down arrow, and then it clears out my entire list for you. Never delete, always clear. You don't want to delete a list because then it just messes everything up. Only clear. So in L1 right now, what you're going to do is type in those 15 numbers. So now, once we have all our numbers in our list, in order to go and figure out your mean and your median and all that stuff, we're going to push the stat button again. We're going to go over to calc, because that stands for calculate. We want to calculate some numbers. And then since you only typed in one piece of information, we typed in one list, you want this first one, the one variable stats. Now, if your screen looks like mine, you're just going to hit enter again, and you will get the numbers. If your screen has this little list over here, the first one needs to say L1, the second one needs to be blank, and then I believe the word underneath it is calculate. So you just keep hitting enter until you get to calculate. And you should get the same exact thing that I have on my screen right now.
Oh, did you do the setup editor thing?
Mm-hmm. You go to stat. Mean. That's our first one. That's our X bar. Now, since they did their weights to the nearest hundredth, let's do our mean to the nearest hundredth. So on your calculator, what is our mean? 1.92. So then for your median, your calculator has this little arrow here because it's telling you, I've got more info. You've got to go down and see it. So then if we arrow down, there's our median, MED, 1.62. Now, it doesn't actually tell you your range. You just have to be able to subtract the numbers. It's your max minus your min. For what? My mean was definitely 1.92. Keep going up. Yeah, you missed a number. So what would our range be? Max minus min? 1.88. You've got your N right in your list. What was our N? 15. First quartile, that's right there with your median. Our Q1 is what? 1.41. Our Q3 was what? 2.45. So then our interquartile range is your Q3 minus your Q1. So 2.45 minus our 1.41. 1.04. Now for our standard deviation, we have to figure out, are we dealing with the full population of trout in the creek, or are we dealing with a sample of it? Sample. So for our standard deviation, we want the one that's the big capital S and then the X. So if we arrow back up, there's our sample standard deviation. So to the nearest hundredth, that would be 0.66. And then our variance is our standard deviation squared. So just use your calculator, 0.66 squared. What do we get? .44, because we're going to go to the nearest hundredth still, so 0.44. So now they want to know how many trout fall within 1 plus or minus standard deviation from the mean. So the way we figure that out is we have to take our mean and we're going to add 1 standard deviation to it to see what the weight would be at that point in time. So 1.92 plus 0.66 gives us 2.58, hopefully is what you got. So at 1 standard deviation above the mean, the weight of a trout is 2.58. We also need 1 standard deviation below the mean, so we would subtract it. So 1.92 minus 0.66 gives us what? 1.26. So what we're looking for to find how many trout are within 1 plus or minus standard deviation from the mean is you're looking for their weight to be between 1.26 and 2.58. So go back up here to my list, count how many trout fall in between that range. 9. So there are 9 trout that are minus 1 standard deviation to plus 1 standard deviation around the mean. And we'll discuss a little bit more what that means when we get in our next couple of classes and we look at a bell curve. All right, number 2, which of the following data sets would have the smallest standard deviation? Do this without the use of your calculator. So to be able to look at a data set and tell if it has a small standard deviation, the numbers would all have to be really close together, because a small standard deviation means that they're all closer together. If you have a large standard deviation, that means your numbers are really far spread apart, so they would be further apart. So of our 4 sets here, which one would be the smallest, do you think? A, because these ones are the closest together. Because numbers closest together. Okay. Running out of time. Gotta move on. So sometimes there are too many data items to write individually, so we use what we call a frequency table. So here in this example, we have marketers are studying the ages of teenagers using certain social media websites. They surveyed 100 teens for a particular site and found an age distribution given in the table below. So the way that we read this is if I'm looking at an age of 13, this 5 over here means that there were 5 13-year-olds. So the old way of doing this, when you put it in your calculator under your L1, is you would type 13 in there 5 times, and you would type 14 in there 11 times, and then 15 in there 17 times. But that just gets pretty tedious. So let's go back to our lists. We're going to clear out our numbers from our last problem so that we have 2 blank lists here. So under L1, you're going to put your ages. So 13, 14, 15, 16, 17, 18, and 19. So then in your L2 goes the other part of your table, the frequencies for those ages. That's our 5, 11, 17, 26, So now you have numbers in both your lists. The only thing is you don't have two different pieces of data. You still have one piece of data. You're still looking at the ages of those teenagers. So when we go to calculate, we're going to go to stat, go to calc, and we're still going to do our one var statistics because we still only have one piece of information that we're looking at. Yes. So if your calculator looks like mine, the way we do this is you're going to hit second and the number 1 to give you list 1. What you're telling the calculator is I have info in list 1. And then comma, second L2, and that's telling the calculator, but I'm giving you my frequencies in list 2. So that calculator knows what to do. If you have the little chart like here, you're actually going to put in for frequency list the L2. You're not going to leave that blank this time. And again, to get L2, you would hit second and then the number 2.
Do we have to put manually in the column? Or does it just go?
No, you have to put them in there. You got it. So A, what is our mean? 16.11. B, 75% of all the data at or below what age? This is a fancy way of asking you, what is our Q3? I know, craziness, but they're asking you. 17. What is our mode? You won't get that from the calculator. You have to look at your frequency chart for that one. Which one has the largest frequency? 16. So our mode would be 16 because it's there the most number of times. Which standard deviation should we use and why? Sample. Why would we use sample? Because they only looked at how many teens? 100. There's a lot more teens out there. So E, how many of the teenagers were more than 2 standard deviations above the mean? So first thing let's figure out is what is our standard deviation? So go to your calculator, look up for our SX. What do we get? 1.53. So next thing we have to figure out is, well, what age is 2 standard deviations above the mean? So our mean was 16.11. I need to add to it 2 standard deviations. So 2 times 1.53. That's not what I got. That's what I got. 19.17 would be the age that is 2 standard deviations above the mean. So if we look at our chart, are there any teenagers that are higher than 19.17? No. So there would be none. None of them are higher than 2 standard deviations above the mean. So what does this tell you about the data? So since there's nothing higher than 2 standard deviations above the mean, this tells us that our data is pretty clustered together. We can also tell that there aren't any outliers. There's no outliers to this data. If you had somebody above 2 standard deviations above the mean, you would definitely have an outlier in there. So then G, a company sampled ages from another site and found the mean was 16.1 with a standard deviation of 2.5. What does this tell you about the other site? Well, pretty much the mean is what? The mean's pretty much the same. Ours was 16.11, so we just rounded a little further. Theirs was 16.1. That's pretty much exactly the same. The standard deviation, however, was what? 2.5 compared to 1.53. It's what? Standard deviation is larger, meaning the ages are more spread out. Your standard deviation is larger. That means you're more spread out with your data. So in this situation, the ages are more spread out apart than the other one. Okay. We got to fly through this last page. So distributions, looking at the shape, the center, and the spread. So this one, if I draw a little curve over this, which I always draw the little curve so I can see what's happening with the data, you've got a little tail kind of over here to the left. So this is what we call skewed left. Because all of your information would be right here in the middle, you're just getting pulled to the left. So it's getting skewed to the left a little bit because it's getting pulled that way. So this one over here would be what? Skewed right, because it's getting pulled over to the right. So when you're talking about your center, your mean is what we refer to as a typical value. We don't like to use the word normal. We say typical. So you want to quote the mean if your distribution is symmetric. If it's skewed, then your mean gets skewed towards that tail. We talked about it. It takes it out of the normal middle part. When you're dealing with spread, you want to talk about the standard deviation if it's a symmetric spread. If it's skewed, you want to talk about your IQR, your interquartile range, which is your Q3 minus your Q1. That gives you the more accurate information versus your standard deviation. So I just want to at least get through these two on the front. We'll deal with the other page on the back one next time if we need to. So first, let's state, is this skewed or is it symmetric? Skewed in which direction? Just left. So what they want you to do is they want you to approximate what would be our mean, what would be our standard deviation. Now we're approximating, so it doesn't mean it has to be exact. Your answers might be a little different than mine. But if it wasn't skewed, our mean would be like right here in the middle at like about 75. But because it's skewed, that means it pulls my mean down. So I'm going to approximate that my mean is about 65. And then our standard deviation, we have a wide spread of data. It's going from 0 to 90, so it's going to be kind of far apart. So I'm going to give it a standard deviation of approximately 10. How about this next one? What's that going to be? All right, so let's just finish this up quick. So this was symmetric. So our mean would be where? Basically right in the middle. So that's going to be at about 35. Since it's not skewed, it's pretty much right in the middle. Your standard deviation, if you notice our scale, it's going up by what? Like a half. So I would say my standard deviation is about a half or a 1, because those numbers are all pretty close together. It's not a very far spread like our first one was.